Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Thermal and Concentration Boundary Layer Thickness of Non-Newtonian Fluids. Before going into the details of today's lecture, what we will be doing, we will be having a kind of recapitulation of what we have seen in last two classes. So, in last two classes we have seen a basics of a momentum boundary layer and then their analysis, and then for the momentum boundary layer or the flow is taking place, boundary layer flows are taking place, and then the conditions are isothermal conditions, that is only momentum transfer is occurring. So, for that boundary layer flows, what is the integral momentum equation, how to derive that one, those details we have seen, and then finally we got this expression integral momentum equation for boundary layer flows, which is valid for both Newtonian and non-Newtonian fluids, right, because the nature of the fluid rheology will come into the picture through this tau information, right. Okay. Then after having this information, subsequently what we have seen, we have developed different expressions, or we have taken different expressions for the velocity profile as function of y, and then we try to obtain what is the momentum boundary layer thickness delta, that is what we have seen, right. So, we have taken two different types of elastic profiles, and then for Newtonian power law fluids and then Bingham plastic fluids, we develop the momentum boundary layer thickness delta. Let us say fluid is power law fluid, and then Vx is given by this expression V naught multiplied by 2 y by delta minus 2 y by delta whole cube plus y by delta whole power 4. V naught is free stream velocity, delta is momentum boundary layer thickness, y is the normal distance or distance normal to the surface, right, from the surface, how in the vertical direction y value increasing, that is what it, right. And then we understand in all these analysis delta is function of x. So, what is the delta for this velocity profile if the fluid is power law liquid is nothing but this one, this is what we got. Then subsequently we also got the drag coefficient for the same case, right. Then we have seen that this if you change the V expression, let us say if you take some other expression for V, Vx, then what you do, you get mostly delta by x, as proportional to the Rex power minus 1 by n plus 1 if it is power law fluid, and then only this constant and then functions of n whatever are there, they are only changing, otherwise mostly they are remaining same, because we have taken other velocity profile also. Vx by V naught is equals to 3 by 2 y by delta minus 1 by 2 y by delta whole cube. This is what we have seen, right. So, now this expression when you have used, we got the similar expression, only this constant has been changed and this Fn function is changing, that is a difference, that is what we have seen. Okay, but Rex power minus 1 by n plus 1 is remaining same, and then Cd also is proportional to the Rel power minus 1 by n plus 1, that is also remaining same, only these constants are changing, or the functions of n whatever are there, they are changing, they are constant if it is a Newtonian fluid, they are function of n if it is a power law fluid. Okay. Rex is the local Reynolds number, and then Rel is the overall Reynolds number based on the length of the plate that we have taken. So, these analysis we have taken a flow parallel to flat plate, horizontal flat plate. Okay. Then we have also seen a few basics of thermal boundary layer, and then we have seen the analysis, and then we have seen how to develop the integral energy equation for the boundary layer flows if there is a heat transfer, that is if the surface of the solid plate and then fluid entering, or the fluid which is flowing over it or this plate are at different temperatures, then heat transfer would also take place within the boundary layer, right. So, then thermal boundary layer would be developing, both the thermal and then momentum boundary layer would be developing simultaneously, right. So, but we have taken the case where they are developing independently or developing independent of each other, because we assume the physical properties are independent of a temperature gradient. Then under such conditions the integral energy equation for heat transfer in boundary layer flows, we got this expression, right. Here the Vx is nothing but the velocity distribution, Vx changing in y direction, how it is changing. T is nothing but the temperature distribution, T function of y. This T naught is nothing but the free stream temperature, delta T is nothing but thermal boundary layer thickness, delta is the momentum boundary layer thickness, delta T is thermal boundary layer thickness, this alpha is thermal diffusivity K by rho Cp, right, and then this dt by dy is evaluated at the surface of the plate, that is y is equals to 0 location. So, this is what we have seen in last two classes. Now, in this lecture what we are going to see, we are going to use this equation, integral energy equation for heat transfer in boundary layer flows, and then try to obtain what is this delta T as function of x. That we can do when we know what is this Vx and as function of y, and then what is this T as function of y. This Vx as function of y we have already seen in the previous lecture how to get and all that. Temperature profile also we try to obtain in a similar way by assuming a third degree polynomial for this temperature distribution, then find out those constants and all that we are going to do. Then substituting them here and then finally simplifying to get this delta T as function of x. But this is going to be much more complicated than what we have done for delta, that is momentum boundary layer thickness, in the previous lecture. The derivation is very lengthy as well as the complicated one. So, we have to be very careful. So, heat transfer in laminar flow of power law liquids over an isothermal flat plate. Flat plate is isothermal condition, but the overall system is having non-isothermality because the fluid temperature is at T naught and then plate temperature is Ts. There is a temperature difference, then obviously heat transfer is there, and then that heat transfer occurring in laminar boundary layer. So, then that within that laminar boundary layer constraint, if both momentum and heat transfer are taking place, so then how this momentum boundary layer thickness is changing in the flow direction, that is as function of x, that is what we are going to derive here. Consider flow of an incompressible fluid at free stream velocity V naught, which is at temperature T naught, over a plane surface maintained at higher temperature Ts, right. Surface temperature and then free stream fluid temperature are provided. Now, at any given distance from the leading edge, temperature of fluid progressively decreases with distance y from the surface because we have taken Ts is higher than the T naught, so, right. So, then this is the plate. So, this is at Ts at higher temperature and this is y direction. So, as we move away in the y direction, right, this T naught, the fluid is at that lower temperature T naught. So, then temperature gradually decrease from Ts to T naught at infinite distance in the y direction. Okay. That infinite distance in reality we cannot have. So, then we are taking that location delta T, which is function of x, by which when y becomes equals to delta T, then the temperature becomes approximately equals to T naught, okay. And reaching T naught at extremity of thermal boundary layer, that is at y is equals to delta T. Actually, theoretically it should occur at infinite distance, but that is not possible in reality. So, that is the reason we are having this boundary layer concept, that is defining a region of fluid or enclosure of a fluid in which the gradients are important, or beyond that one the gradients are negligible. So, that boundary whatever is there in which the concentration gradients or temperature gradients are existing, that we call as a boundary layer flow, and then that is also changing in the x direction function of x, that is flow direction. That is at the leading edge boundary layer thickness is 0, and then as x increases boundary layer thickness increases, whether it is momentum boundary layer or thermal boundary layer. That is what we have seen. So, now what we assume, temperature profile is having a third degree polynomial of this form, T is equals to a plus by plus cy square plus dy cube. Now, if this a, b, c, d you can find out, then obviously you can use the final temperature profile in this momentum in this integral energy equation here, and then get the dt by dy at y is equals to 0 and then substitute here, and then finally solve this equation delta t as function of x, right. So, first what we have to do, we have to find out this a, b, c, d constants. So, obviously we need to have boundary conditions. So, boundary conditions what we are having, we are actually if you recollect, we have a solid plane like this, flat plate, the fluid is coming and then approaching the plate and then flowing like this. So, this is vertical direction is y direction, horizontal direction is x direction. So, this is at y is equals to 0 location, temperature T is equals to Ts, that is given, and there is a thermal boundary layer within the laminar flow region. Forget about the momentum boundary layer as of now, that is not required, right. So, this thermal boundary layer thickness changes with x, that is increases with x in the flow direction, because as x direction increases, the fluid element experiences more retardation and all that we have already seen. So, at this y is equals to delta t onwards, t is equals to t naught and then dt by dy is equals to 0. Temperature becomes equal to the free stream temperature is T naught, free stream velocity is V naught, right. And then from this point onwards, at y is equals to delta t onwards, dt by dy is equals to 0, that is gradient becomes 0. And then at the solid surface here, what we have constant flux, dq is constant, this is what we know. So, dq w by dy should be 0, and then qw is nothing but minus k dt by dy. So, that means d square t by dy square is equals to 0 at y is equals to 0. So, at y is equals to 0 we have two boundary condition, at y is equals to delta t we have two boundary conditions for the temperature. So, we use those four boundary conditions to get these four constants from this equation number 1. So, at y is equals to 0, t is equals to Ts, if you substitute t, what we have taken, t is equals to a plus by plus cy square plus dy cube, which is nothing but our equation number 1. So, now here if you substitute y is equals to 0, so you get right hand side only a and then left hand side t is equals to Ts. Then at y is equals to delta t, that is at the thermal boundary layer location, t is equals to t naught. So, here in place of y right side we are substituting delta t. So, then we have this equation. Then at y is equals to delta t, dt by dy is 0, that is the other boundary condition at y is equals to delta t. So, dt by dy is what? dt by dy is nothing but b plus 2cy plus 3dy square. So, now here in place of c you substitute delta t here. So, then you get b plus 2c delta t plus 3d delta t square is equals to 0, because dt by dy is equals to 0 at y is equals to delta t. And now at y is equals to 0, d square t by dy square is equals to 0, we are having d square t by dy square is what? It is nothing but 2c plus 6dy. So, now here if you substitute y is equals to 0, so then this is gone, that is 2c is equals to 0. That means c is equals to 0 and then a is equals to Ts, and then remaining these equations 3 and 4 if you solve for b and d constants, b you will get 3 by 2 T naught minus Ts by delta t, and d you get minus 1 by 2 T naught minus Ts by delta t cube, right. So, when you substitute these equations in this equation number 1, what you get? T is equals to a is nothing but Ts, and then b is nothing but 3 by 2 T naught minus Ts by delta t, c is nothing but 0, and then d is nothing but minus 1 by 2 T naught minus Ts by T naught minus Ts divided by delta T cube. So, that means T minus Ts divided by T naught minus Ts is nothing but 3 by 2, this y is already here and then y cube is here. So, 3 by 2 y by delta T minus 1 by 2 y by delta T whole cube you are getting. So, that is you get here this one. So, T minus Ts we are designating by theta, T naught minus Ts we are designating by theta naught, right. So, this is temperature profile you got already. Now, you need to get dt by dy at y is equals to 0. So, thermal boundary layer thickness of power law fluid flowing over a plane surface we take. Here integral energy equation is this one. Fine. Velocity profile already we have taken this one in the previous class, because we cannot do the momentum boundary layer derivation again for a different velocity profile, because this equation when you substitute T naught minus T and dt by dy and Vx in this equation number 7, you also find that delta terms are there. So, that delta derivation we should have already done. So, for this velocity profile, this delta, that is momentum boundary layer thickness as function of x, this is already we have done in previous class. So, that we can adopt as it is. So, temperature profile just now we have taken this one. So, remember whatever the derivation that we are going to do in order to get this delta as function of x, that is valid for these two velocity profiles and then temperature profiles given by equation numbers, this equation and this equation. If you change any of these two equations or both the equations, the derivation is going to be different and then final results are going to be different, especially those function of n is going to be different. Maybe Reynolds power 1/3 and Prandtl power 1/2 etc., those terms would be there, they will be as it is, they may not be changing. So, you have to be very careful which velocity profile you are doing, because we are doing it for two different velocity profiles and then two different temperature profiles, because in the at the end of this class we are going to take a different velocity profile and then see the answers, final answers of the delta T. Okay, anyway, so now if you take this velocity profile and then this temperature profile, what is delta T as function of x, that we will see first. So, we need to have T naught minus T. So, what we do, this equation both sides we multiply by -1 and then add +1 either side. So, 1 minus T minus Ts by T naught minus Ts is equals to 1 minus this one. So, that is when you do the LCM you get T naught minus Ts minus T plus Ts. So, that is T naught minus T, you get T naught minus T divided by T naught minus Ts. So, that divided by T naught minus Ts, that I have taken to the right hand side, the terms of right hand side are as it is, right. Then we also need dt by dy. So, this expression, if you do the dt by dy, this expression what you get, dt by dy is equals to T naught minus Ts multiplied by 3 by 2 delta T minus 3 by 2 y square by delta T cube, this is what you get. And then if you do delta T at y is equals to 0, then what will happen, this y terms are there, so second term is gone, only thing that you get 3 by 2 T naught minus Ts divided by delta T. So, T naught minus Ts we are writing as theta naught. So, now in order to substitute or simplify this equation number 7, we need Vx, we need T naught minus T and then we need dt by dy at y is equals to 0, all of them we got it now, right, by equation 8, 9 and 10. This equation 8, 9, 10 we are going to substitute in equation number 7 now, right. Equation number 7 is rewritten here. So, d by dx of integral 0 to delta t, Vx is nothing but this one, and then T naught minus T is nothing but T naught minus Ts, that is theta naught multiplied by this one, dy is equals to dt by dy at y is equals to 0 is nothing but 3 T naught minus Ts, that is theta naught divided by 2 delta T and then multiplied by alpha. So, what we can do now, this theta naught we can cancel out. This V naught is a constant, free stream velocity, constant velocity, that we can take to the right hand side. So, and then remaining terms here whatever are there, these two terms we are multiplying and then we are writing like expanding these terms like 2 y by delta minus 3 by 2 y by delta multiplied by 2 y by delta. So, you get 3 y by delta t y by delta. So, you have to be very careful about delta t and delta, right. So, both the terms are there here, right. Next step what we do? Next step we integrate. When we integrate with respect to y, so in place of y here you get y square by 2, here you have y square. So, y cube by 3 you get, here y power 3, so y power 4 you get, like that all the terms you get, right. So, that when you do y square by 2, y cube by 3, y power 5 by 5, y power 4 by 4, y power 5 by 5, y power 7 by 7, y power 5 by 5, y power 6 by 6 and then y power 8 by 8 are there. That is what we get after integration. Remaining terms are constant, we are keeping as it is, limits 0 to delta t and then right hand side term as it is, we are not doing anything, right. Next term what we are doing, we are substituting the limits, right. So, here this 2 and this 2 is cancelled out. So, 1 by delta y square, now delta t square. Next term is these 3 cancelled out. So, 1 by delta as as it is and then in y cube. So, delta t cube by delta t square. Next term 1 by delta 1 by 5 as it is, then delta t power 5 by delta t cube. So, delta t square you get. Next step here 2 1 ja 2 2 ja. So, 1 by delta cube 1 by 2 as it is and then y power 4. So, after substituting the limits delta t power 4, then here 1 by delta cube 3 by 5 as it is and this y power 5 is now delta t power 5 divided by delta t. So, then you get delta t power 4. So, like that remaining terms also done here like this and then we take delta t by delta is equals to epsilon which is less than 1, that is for the Prandtl numbers are very large or the high Reynolds number, high Prandtl number flows where the boundary layer thickness are thinner and then especially thermal boundary layer thickness is smaller compared to the momentum boundary layer thickness. That case we are taking. So, then here d by dx and then from all the terms what we are taking delta we are taking common. So, this term and then this term are same with plus and minus sign. So, then that is 0. So, remaining terms now here delta if you take common then what we get, already 1 by delta is there. So, 1 by delta another 1 by delta will be there. So, delta square would be there. So, delta t square by delta square I am writing epsilon square by 5. Then here this term 1 by 2 delta t power 4 by delta power 4, that is epsilon by epsilon power 4 I can write like that. Remaining terms also I can write like this here, right. Next step what I do, since epsilon is less than 1, epsilon power 4, epsilon power 5, epsilon power 6 and so on, so higher power terms would be negligible, would be having small contribution compared to the epsilon or epsilon square term. So, what we can do, we can strike off these terms and then take only epsilon square terms. Then what we have, d by dx of delta epsilon square by 5 is equals to 3 alpha 2 v naught delta t. In place of delta t I am writing delta multiplied by epsilon, because epsilon we have defined as delta t by delta. So, now this is the simplified equation. So, this equation you can simplify to get delta t as function of x, because for the velocity profile whichever we have selected, what is delta is also known. We have done derivation in previous class, that we can adopt here, right. So, before that what we do, we further simplify this equation. So, this 5 I have taken to the right hand side. So, then I have 15 alpha by 2 delta v naught epsilon. Now, this delta and then epsilon, both of them are function of x. So, when you differentiate this one, you get epsilon square d delta by dx plus 2 epsilon d epsilon by dx multiplied by delta as it is equals to right hand side term as it is. Next what I am doing, this whatever delta epsilon in the left hand side in the right hand side is there. So, that I am taking to the left hand side. So, that I have delta epsilon cube d delta by dx plus 2 epsilon square delta square d epsilon by dx is equals to 15 alpha by 2 v naught. So, right hand side now completely a constant. Okay. Now, let z is equals to epsilon cube. Now, here this is all a mathematical simplification in order to solve this equation. This equation we have to solve to get delta t as function of x for a known delta as function of x. Delta is known as of now, we have already done the derivation. So, we adopt it as it is. So, if you take z is equals to epsilon cube, dz is equals to 3 epsilon square by d epsilon, but here we need 2 epsilon square d epsilon by dx. So, from here dz is equals to 3 epsilon square d epsilon. If I do divided by dx, I get dz by dx in the left hand side, right hand side d epsilon by dx I will be having, and then 3 epsilon square as it is. But I need 2 epsilon square d epsilon by dx for this term to substitute here, right. So, that what I am doing now, both sides I am multiplying by 2 by 3. So, that 2 by 3 dz by dx would be nothing but 2 epsilon square d epsilon by dx. Epsilon cube is nothing but z. So, those things now we substitute here. Before substituting, we also enlist what is delta, because we need to substitute delta also. Delta as function of x, this we have derived in the previous lecture. So, we are taking directly. So, delta from this one is nothing but this is function n we are calling. So, that function n multiplied by Rex for the power law of fluid is nothing but rho v naught power 2 minus n x power n by m whole power minus 1 by n plus 1, and then left hand side x whatever is there, that we have taken right hand side. Fn is nothing but this one, this quantity we are calling Fn, right. So, we also need d delta by dx also to substitute in the previous equation. So, now delta simply in a simple way I am writing a Fn whatever the other than x power these terms are there. So, other than these terms I am writing that as a multiplied by Fn. A is nothing but rho v naught power 2 minus n by m whole power minus 1 by n plus 1. So, the remaining term x power 1 minus n by n plus 1, that is what I am having. So, that is delta is equals to Fn a x power 1 by n plus 1. Now, d delta by dx, from here you get a Fn 1 by n plus 1 x power 1 by n plus 1 minus 1, that is x power minus n by n plus 1. So, now we have all the quantities to substitute in the equation number 11. So, now those equation numbers 12, 13, 14 we are going to substitute in equation number 11. This is equation number 11. Delta is a Fn whatever x power is there 1 by n plus 1 we are writing as it is. Epsilon cube is nothing but z. D delta by dx we got a Fn by n plus 1 x power minus n by n plus 1 plus delta square is nothing but a Fn x power 1 by n plus 1. So, square is there. Then remaining terms are 2 epsilon square d epsilon by dx is nothing but 2 by 3 dz by dx, right. Right hand side as it is. Z is nothing but epsilon cube, that is what we are taking. So, this equation what we are trying to do, we are now here the combining the x terms. So, x power 1 minus n by n plus 1 you will be having this a Fn we are having 2 times. So, a Fn whole square and then 1 by n plus 1, z is as it is x power 1 minus n by n plus 1 we are having. Here a Fn whole square we are writing, and then x power 2 by n plus 1 2 by 3 dz by dx right hand side as it is. So, next step this a Fn whole square that we have taken to the right hand side, remaining terms are as it is. Now, I want this one, this equation in the next step I want only dz by dx, I do not want any multiplication of this thing for dz by dx term. So, for that what I am doing, I am multiplying this equation both sides by 3 by 2 x power minus 2 by n plus 1. This is what I am doing. So, that this will become on multiplying this and this will become 1, I have dz by dx, and then remaining terms we are writing like this. So, dz by dx plus 1 by n plus 1 x power 1 minus n by 1 plus n, and then z were as it is, this 3 by 2 x power minus 2 by n plus 1 we are multiplying, right hand side this term is as it is, and then this is the new term that we are multiplying, right. So, next step what we do, we further simplify this equation by combining these two x terms. So, x power 1 minus n minus 2 by 1 plus n, that is what you get, minus n minus 1, that is you get x power minus 1. So, that is I am writing in the denominator as x here, remaining all other terms are as it is. So, now this is a differential equation which is having a standard form dy by dx plus py is equals to q, where p and q are functions of x. So, that the solution of this equation will become y multiplied by integration factor is equals to integral of q multiplied by integration factor plus integration constant. So, what is the integration factor? If is nothing but exponential of integral p dx. So, now here that we do compare. So, y is equals to z here, x is nothing but x, and then p is nothing but whatever this function other than z, whatever this is there. So, that is p, and then right hand side term is entirely is q. So, here integration factor e to the power of integral of p dx, p is this one. So, when you do the integration of this one, e to the power of 3 by 2 n plus 1 is as it is, dx by integral of dx by x is nothing but ln x, right. So, that is I can write e to the power of ln x power 3 by 2 n plus 1. So, e to the power of ln, that will be cancelled out, only whatever x power 3 by 2 n plus 1 is there, that would be there as integration factor. So, the solution would become here z multiplied by this if is equals to integral of this is q multiplied by if plus c, right. So, now this here these two terms we are combining, x terms we are combining, so that we can do the integration, remaining terms we are keeping as it is. So, here we get x power minus 1 by 2 n plus 1, and then when you do the integration of this one, x power minus 1 by 2 n plus 1 plus 1 divided by minus 1 by 2 n plus 1 plus 1, right. So, next step what we have, this is what we have, constant c is as it is. So, next step what I am doing, this whatever x power this is there, that also I am taking to the right hand side. So, x power minus 3 by 2 n plus 1 is there. So, that and then this term we are combining together. So, that x power 2 n plus 1 minus 3 by 2 n plus 1 I can write, and then c is being multiplied by x power minus 3 by 2 n plus 1, right. So, now here this is nothing but when you do the simplification, you get 2n minus 2, that is 2 multiplied by n minus 1, 2 you can cancel out. So, that you have this term, right. Remaining terms are as it is, we are not doing anything with the remaining terms. Now, this z we got, which is nothing but epsilon cube, and then epsilon cube is nothing but delta t by delta whole cube, because epsilon is nothing but delta t by delta. So, still the solution is not complete, we are only in the halfway, because this delta cube also we have to take to the other side and then do the lot of simplification, though it looks like almost we are at the end of the derivation, but still half the way we have to go. So, in this equation, just recapitulating, this a is nothing but this one. So, a square would be this one. Why? Because we will be substituting all these things and then writing terms again now in terms of Reynolds number or Prandtl numbers or both. for that reason now we are going to substitute this a here. So, this a square I have written rho v naught power 2 minus n by m whole power minus 1 by n plus 1 whole square. So, power minus 2 by n plus 1 is there, all other terms are as it is. Then this term what I am doing, I am multiplying x power minus 2 by n plus 1 and then dividing by x power minus 2n by n plus 1. So, that in the denominator x power n whole power minus 2 by n plus 1 I can write, and then that x power n if it is combined with rho v naught power 2 minus n divided by m. So, that is rho v naught power 2 minus n x power n divided by m you get, and then whole power minus 2 by n plus 1 you get, and this is nothing but your Rex for power law liquids local Reynolds number. Okay. Rest all other terms are as it is. So, that when you write, so Rex power minus 2 by n plus 1 we are having, and then whatever this delta cube is there, that also I have taken to the right hand side. So, delta is nothing but Fn Rex power minus 1 by n plus 1 multiplied by x. This is nothing but delta. So, delta cube is there. So, the same thing is coming here also to the constant. So, but this we do not need to worry, because at x is equals to 0, delta t is equals to 0. So, from applying this leading edge boundary condition you get c is equals to 0. So, all this term altogether the second term in the RHS would be 0. So, we can take only this term and then further do the simplification. So, when you do that one, you have this one, this term, because here this when you combining these x terms, x power 3 and then this x power minus 1 minus n by n plus 1 and then this plus 3, when you combine it you get x power minus 1 minus n plus 3n plus 3 by n plus 1. So, that is x power 2n plus 2, that is 2 multiplied by n plus 1 divided by n plus 1. So, this n plus 1 cancel out. So, you get x square. So, these two terms when you combine this term and then this x cube term you get x square from this simplification. So, rest all other terms are as it is. So, that x square is coming here. Similarly, this Rex power minus 3 by n plus 1 and then multiplied by Rex terms also, if you simplify Rex power minus 3 by n plus 1 and then plus 2 by n plus 1 you get Rex power minus 1 by n plus 1. So, this constant multiplied by Rex power minus 1 by n plus 1 x square you will be getting. So, that is what, right. So, now we take cube root either side so that we can have delta. So, this all these constants whatever are there. So, and then functions of n we are writing together and then taking cube root, that is power 1 3 we are taking 1/3. Fn is there, whatever Fn is nothing but this 315, Fn is nothing but 315 n plus 1 2 power n divided by 37 whole power 1 by n plus 1. So, cube root of this one, so this 3 is there, and then Rex also this 1 by 3 is there, and then x also 1 by 3 is there, right. Now, this 45 multiplied by 2 90 by 4 n plus 1 by 2 n plus 1, and then this Fn also I am writing here again once again no problem, whole power 1 by 3, and then this alpha divided by V naught, alpha divided by V naught power 1 by 3 as it is. Now, I am multiplying by x power 1 by 3 and then dividing by x power 1 by 3. So, that here I can have alpha by x V naught power 1 by 3, and then whatever x power 2 by 3 and then x power 1 by 3 is there, that I can write x power 2 by 3 plus 1 by 3, that is x. So, that this x I can take to the left hand side, so that I can write delta t by x is equals to this form, right. So, this more or less you can take it as a final solution, but still we have to do some more simplification, because we know for a Newtonian fluid the thermal boundary layer thickness or subsequent Nusselt numbers that you have. So, they are having Rex power minus 1 by 3 and then Prandtl number minus 1 by 2 etc., those terms are there. So, Rex terms are there, Prandtl number terms are not here. So, that modification we are going to do now. So, that equation, previous equation what I have done, alpha in place of alpha by x v naught we were having. So, in place of alpha I am writing k by rho Cp, remaining all terms are as it is, right. Next step what I am doing, I am writing k by Cpm here, and then x by v naught whole power n minus 1 and then the power 1 by 3 is there. So, the remaining what k I have taken, Cp I have taken from this parenthesis terms. So, remaining terms are 1 by rho x v naught. So, 1 by rho x v naught whole power 1 by 3. So, here, but additionally what I am doing, I am taking x power n minus 1 divided by v naught and then 1 by m. So, the inverse of those terms I have to multiply. So, x power v naught whole power minus n minus 1 by 3 and then m power 1 by 3 I am multiplying. Okay. Whereas the Rex term is as it is. Why am I writing this one? Because this is nothing but Prandtl number inverse for a power law fluid, right. So, here this in place of Prandtl number power minus 1 we can write. So, that is Prandtl power minus 1 by 3. This is also local Prandtl number because it is defined as x, right. Prandtl number for Newtonian fluid what you have, Cp mu by k. So, in place of Cp by k as it is, in place of mu what you can write, m then v naught by distance x power n minus 1, this is you can write it as effective viscosity. This is nothing but mu effective for a power law fluids. So, that is whatever Cpm by k and then v naught by x whole power n minus 1 is there, that is nothing but Prandtl number. So, we are having inverse of Prandtl number and whole power 1 by 3. So, Prandtl x power minus 1 by 3 and then remaining terms I am just expanding and then combining any similar terms are there. So, 1 by rho whole power 1 by 3, this 1 by v naught power 1 by 3 here I am having, and then here 1 by v naught whole power minus 1 minus n minus 1 by 3 are there. So, then power 1 minus n minus 1 by 3 I am here writing, and then here x power minus n minus 1 by 3 is there and divided by x power 1 by 3 is there. So, then power minus 1 by 3 I am writing here, m power as it is I am writing, m power 1 by 3 as it is I am keeping. Why? Because, so when I further do this is nothing but I get 1 by v naught power 2 minus n by 3 and then this x power minus n by 3 and then this m power 1 by 3. So, then here if 1 by 3 whole power 1 by 3 is there. So, what I can do from here, I am having rho v naught power 2 minus n x power n divided by m whole power minus 1 by 3 I can write, isn't it, right. So, when I am writing these terms combining joining together like this, rho v naught power 2 minus n x power n by m whole power minus 1 by 3. So, now again this is nothing but Rex. So, Rex power minus 1 by 3 you are having, right. So, that we are substituting here. So, this term I am writing Rex power minus 1 by 3 and then this Rex power minus 1 by 3 n plus 1. So, now when you combine them you get Rex power minus n plus 2 divided by 3 n plus 1. right. So, this is the final expression that we have, right. So, now here if n is equals to, if n is equals to 1, then what is this delta t by x is some constant Prandtl x power minus 1 by 3 and then Reynolds x power minus 1 by 2 you get, because whatever nu x or nu average etc., that you expressions that are there, they are obtained from after using this expression in those definition, right. That is we are going to do anyway now. So, here as I already mentioned, Cp m by k V naught by x whole power n minus 1 is nothing but local Prandtl number, fine. So, if the velocity and temperature profile are taken as differently, so the temperature profile we are keeping same as whatever we have derived today's lecture, but the velocity profile we are taking this one, different one. In the derivation until now whatever we have done, the Vx by V naught is a different expression. So, now I am changing only the velocity profile, but temperature profile I am keeping same. Then do the same analysis, delta by x you get this one which we have already derived in yesterday's lecture, at least because yesterday for this profile as well as the other profile we have developed the momentum boundary layer thickness. So, this we know. So, delta t by x when you do you get this expression. You can see Prandtl power and then Reynolds number powers, they are not changing, only these constants or function of n they are only changing, right. So, where here Gn is this one and then Rex is this one, Prandtl x is this one, same thing. So, this you take it as take home problem, because again if we do the entire thing it will take 1 class again. So, this at least similarly the way that whatever derivation that we have done today, similarly you can do and then you get this one, right. So, now for this velocity profile and then temperature profile, heat transfer coefficient H if you wanted to know. So, H delta T is equals to minus K dt by dy at y is equals to 0, that balance if you do the heat transfer by the convection and then heat transfer by the conduction at the interface, then you can find out what is this H. dt by dy already you got it as 3 T naught minus Ts by 2 delta T from this expression, right. This is what you get by substituting dt by dy and then substituting y is equal to 0, this is what you got. You get, we already done also a few slides before. So, then H you will be getting minus K 3 T naught minus Ts by 2 delta T, whatever the left hand side Ts minus T naught was there, that we brought to the right hand side. So, this is cancelled, 3 K by 2 delta T you are having. So, delta T for this combination of velocity profile and temperature profile is nothing but this one. So, H you will be getting this one after substituting delta T here, then rewriting. So, you will get this one. So, now here from this equation what you do, H, x and k of right hand side terms you take to the left hand side, H x by k if you do, then you get 3 by 2 Prandtl power 1 by 3 and then Re power n plus 2 divided by 3 n plus 1 and then this whatever the constant as it is. So, this Hx by k is nothing but nu x, local Nusselt number. So, that is what we have written here. So, that is the local Nusselt number is this one Hx by k, rearranging the previous equation, that is it. So, this is the local Nusselt number, that is local Nusselt number in the sense this is the plate we are having, this is y is equals to 0 and then y is equals to gradually increasing, this is the boundary layer is having. So, at different x values, x direction, what is the Nusselt number here, here along the plate surface, that you wanted to know, then you have to use this equation. Okay, then you have to use this equation along the plate length. As the x value increasing, how the Nusselt number is increasing, that you can get from this number. But if you wanted to know the overall Nusselt number, average for the overall entire length of the plate, then you have to do the integration of this one, and then you have to do the integration of this one, and then divide by integration of the distance dx, and then integration 0 to L. This is what you have to do. This we are doing in the next slide here anyway. So, from here this equation 19, what we are finding, h is proportional to the x power minus n plus 2 by 3 n plus 1. How do you get? So, now here all these terms, whatever this h is equals to this expression is there. Now, Prandtl number also you expand, Rex also you expand. So, here whatever these x powers are there, that you get as this one. So, h is proportional to x power minus n plus 2 by 3 n plus 1, that is what you that is what you will get. You can do the simplification. So, if you substitute n is equals to 1 in this equation 19, you get Nusselt number is equals to this one. You might remember this correlation for Nusselt number for a flat plate, that you might have by hearted or remembering in the fluid mechanics or heat transfer course. So, the derivation is coming like this. So, we have done for the power law case as a generalized one, so that n is equals to 1 I can substitute, I can get the Newtonian solution as well. So, that by one derivation I can get the two solutions. So, in this equation 19, if you substitute n is equals to 1, this is what you get. So, if you wanted to know the mean heat transfer coefficient and mean Nusselt number, Hm, that is mean heat transfer coefficient, is integral 0 to L h dx by integral 0 to L dx you have to do. H already you got this expression, right, okay, except this L, that is the x. So, now x terms are there only in this Prandtl power x power 1 by 3 and then Re x power n plus 2 by 3 n plus 1 and divided by x, right, whole divided by integral dx 0 to L, that is coming out L, that we have written like this. So, now here again you expand this expressions for Prandtl x and then Rex, and then you write x terms, remaining terms you keep constant, and then do the integration, substitute the limits 0 to L, then finally you get this expression, whatever the 9 k by 9 k n plus 1 by 2 L and 2 n plus 1, and then all this one you get. So, that equation you rearrange Hm, that k by L you take to the left hand side. So, Hm L by k, if you write, you get NUM. So, that is nothing but this one. Now, here after substituting the limits, what you get, x place in place of x you will be getting L. So, then these Prandtl numbers and then Reynolds number would be based on the entire length of the plate. Okay. So, that is REL is equals to rho V naught power 2 minus n L power n by m, not x power n, L power n, and then Prandtl number L you will get Cp m by k V naught by L whole power n minus 1, not x whole power n minus 1. So, they are the Reynolds number and then Prandtl number for the entire geometry, not the local one. Fine. So, that is all about the thermal boundary layer thickness and then corresponding heat transfer coefficients and then Nusselt numbers, both average heat transfer coefficients and then mean heat transfer coefficients and then average Nusselt numbers, local Nusselt numbers, etc., those derivations we have done. With that, we complete the thermal boundary layer thickness of non-Newtonian fluids as well, right. Now, what we do, we see concentration boundary layer thickness of non-Newtonian fluids. So, but we are not going to do all the derivation as we have done for the momentum and thermal boundary layer cases. We take a thermal boundary layer case and then analogously we write a concentration boundary layer case, right. So, mass transfer in laminar boundary layer flow of power law liquids. Basic equation for molecular diffusion by Fick's law is nothing but minus DAB dCA by dy. I am writing Na, some books write GA and all that, do not worry, that is a notation. So, Na is mass transfer rate per unit area, that is mass flux. If you are writing in moles, then it is molar flux, kilomole per meter square second. DAB is molecular diffusivity, which is in meter square per second, and then analogous, this is analogous to Fourier's law of heat conduction. So, that we already know that it has Q is equals to minus alpha d by dy of rho Cp T, right. So, now when you compare equation number 1 and 2, they are similar to each other, they are similar to each other. So, only thing that in place of alpha you can write DAB, in place of rho Cpt you can write Ca. Okay. Then integral equation in a similar way we can write like this: integral species conservation equation. So, what we have done, in place of Vx it is as it is, in place of Ts minus T, what we are writing? We are writing CAS minus CA dy, okay, and then in place of delta T we are writing delta M, that is concentration boundary layer thickness delta M, and then in right side in place of alpha we are writing DAB, in place of dt by dy we are writing dCA by dy, because here rho Cp would also be there, but that rho Cp is there in the left hand side also. So, that has been cancelled out, that is it. Okay. So, then analogously species conservation equation, integral species conservation equation for boundary layer flows, this is only for the boundary layer flows, we can write like this. So, now similarly as we did for the thermal boundary layer case, if you know Vx, if you know Ca, then you can find out the concentration boundary layer thickness delta M as well. Okay. So, but we are not going to do that one because the equations are similar, so their solutions would also be similar. So, temperature difference, what we had taken T minus T naught by Ts minus T naught is equals to 3 by 2 y by delta T minus 1 by 2 y by delta T whole cube we got by taking T is equals to A plus By plus Cy square plus dy cube expression or third degree polynomial expression for the temperature. Similarly, for the concentration also, if you do if you take third degree polynomial expression, that is Ca is equals to A plus By plus Cy square plus dy cube, and then apply the 4 boundary conditions, 2 at y is equals to 0 and 2 at y is equals to delta M, and then simplify. So, you get exactly the similar expression like a temperature profile, only thing that in place of delta T you have delta M and in place of T you have C. Okay. So, obviously the results are going to be similar. So, delta M by x you are going to have this expression, only thing that in place of Prandtl number you get now Schmidt number, right. So, mass transfer coefficient also Hd in a similar way, if you do balance, that is mass transfer by convection is balanced by the mass transfer by diffusion, then you have an expression for Hd that is given by this one, and delta M just we have written equation number 5 previous slide, that you substitute here. So, you get that one, and then you do all the simplification rearrangement. So, then you get the local Sherwood number, which is similar to local Nusselt number in the case of thermal boundary layer flows. So, that is what you get here, but you have to careful that here now you get the Schmidt number rather than the Prandtl number, because mass transfer boundary layer that we are considering. So, average Sherwood number along the length of the plate, along the entire length of the plate from x is equals to 0 to x is equals to L, the average Sherwood number would be this one, right. So, where here SCx is the local Schmidt number given by m by rho DAB V naught by x whole power n minus 1. This is again for power law liquid, okay. And then SCl is nothing but the overall Schmidt number for the entire geometry based on the length of the plate, and then this is also for the power law liquids, right. Remember here also one more important thing, that delta m and delta are independent of each other. As we have considered in the case of delta T and delta, okay, then only these results are valid, because we are writing analogously for this case with the comparison with the delta T case. Okay. So, delta T case that we have derived assuming that delta that is assuming that the momentum and thermal boundary layers are independent of each other. Similar way in the case of concentration boundary layers as well, the concentration boundary layer and then momentum boundary layer are developing independent of each other, or they are not interfering each other. The concentration gradients are maintained such a way, right. Like in the case of thermal boundary layer case, the temperature difference or temperature gradients are maintained such a way that they are not disturbing the, or they are not changing the physical properties significantly, right. So, this is the last lecture of the course. The references are provided here for this course, but the most of the details I got from these reference books, but anyway derivations are not available any of the books, we have to do carefully, right. Thank you so much for your kind cooperation throughout the course.